I'm Dan Daly. I've been working at Intel doing these sort of hardware offload functions for several years now. And we've been able to benefit from being able to try it once and kind of see what works and what doesn't, and then be able to come and iterate on that over time. And so I think today I'm going to talk about a little bit about why we made certain decisions about how we did hardware offload. And then in the next session, Deb Chatterjee is going to talk to you a little bit more about the details of how we went and implemented it. And this picture here is just a sort of my overly simplistic view of kind of what we're trying to do. We have the host on one side that might be virtualized, there might be containers, and it has to get to the network, it has to go and talk to everyone else it wants to talk to. But with Open vSwitch, we've wedged something in between so that we can do a bunch of features that you don't have when you just have a regular wire. And these features are sort of why OVS is there today. And so you have an interface that the VM or the container or the system talks to. You have security to make sure that the traffic going in and out of that interface is what you expect. You have virtualization because that VM might have no idea what the network actually looks like. They only have their network. And then you have visibility, and this is sort of on the backside of the system. If I'm managing hundreds of thousands of VMs and containers, I want to know how the traffic's coming in and out. I want to be able to look at it when it's broken, and I might want to know if it's just up or down. And lastly, one thing that OVS has been shown to be really good at is to be able to hide the redundancy that might be in the system. So you might have a server that has just one wire coming out of it. You might have a server that has 2 or 4 or something like that, and you might use different techniques to do that redundancy. And once the network is virtualized, then the VMs and containers don't need to be privy to that as to how you did your redundancy. And so I just picked my 5 favorite features from OVS and maybe 5 things that are challenging when you do hardware offload. And so the question is, how do I keep all of that goodness and go faster and maybe go easier or go better? So how many people in here have experimented with hardware offload, in college or something? Yeah? Okay, cool. And so in the past, it's been, when we first started out, we just wanted to go fast, and that was the main goal. And we kind of went in and had to go and try to fix some of the things that we lost after the fact. And so this is my maybe not so fair picture of how the first time we tried hardware offload it kind of looked like. We had a separate hardware interface that you had to plumb into the VM, or maybe you handed it to the container. And that was the virtual function that was part of the hardware. And then the hardware might have a completely different way to do virtualization. It might only be able to do certain tags, certain end caps, things like that. And then sort of accidentally, a detail in SRIOV made redundancy very difficult. If I passed a VF into a VM, that VM could only send traffic out of a particular uplink in the network. So it wasn't very virtual, because I've now have to run some redundancy in the VM potentially, and that was sort of a black eye on SRIOV. And so, but it still worked, and it went it was very fast, and it also had a really interesting feature was that I could hardware isolate each one of these VMs or containers. They each got their own port, and there was no sort of shared memory, or there was no sort of way to get in between that VM and the hardware. It was a direct line right into that endpoint. The second, or maybe one of the more difficult issues that we had with hardware offload was that you might have something that you need to check on the packets before you let them fly. And so what we had to do was we had to take certain packets out of the pipeline and pass them through a security check. Sort of say, hey, you know, are these packets okay? And we still do that in software. And so you end up with this, it used to be just a nice linear packet pipeline, but now you have all these specials. All these special paths that happen. Sometimes you have a special interface just for hardware. Maybe you have a special way to handle your redundancy. Maybe you need a little process running on the host just to handle the security. And all of that goodness that you had, it starts to degrade. And some of the other things that we did was we said, well, maybe we'll just do software and hardware. Sort of a common solution we have is like, all right, we can't decide if it should be software or hardware. They both have values. So we'll pass it to the software, we'll pass it to the hardware, and maybe he'll pass it back to the software. And what we found was that sometimes was worse, where we involved the hardware in trying to do some of the functionality, but the need to keep those different multiple pipelines together and synchronized was a lot of overhead. And so I would say after that first attempt, you know, I would set up 2 simple rules. Rule number 1 is no specials. If it's hardware offloaded, you shouldn't know about it. It should just go faster. And these are ideal rules. But this is where you want to land. You don't want to have any hardware specials, no special interfaces, no special cases that only hardware offload runs into. And the second one is just the title of my talk, which is it's all or nothing in that if you just offloaded about 80% of it, but then had to hop back into software for the other 20%, what we found is that sometimes can completely sort of negate some of the benefits that you got from the hardware offload. And so we try as best we can to get all of the same functionality that we had in the software and push it into the hardware. And yes, that makes it much harder to design the hardware. This is probably why this is taking a little bit longer to develop in terms of hardware offload. But once you have all of the feature set that you want in the hardware with all those same 5 things, then you sort of finally realize the benefit of being able to use hardware to do these open vSwitch functions. So how do we follow the rules? There's only 2 of them, so let's see. So another interesting use case of this hardware offload is that we can support both a virtualized server that might be chopped up into little tiny pieces and sold individually, or a lot of cloud vendors are selling the entire server, like the whole chicken, where you sold the server, and what we're going to do is we're just going to put virtual interfaces into that server. There's a networking virtual interface, there might be a storage interface, and for our use case, we want to be able to support both. And ideally, if the product can switch between the 2, that'd be great. And so given the need to have both of those use cases, what do we do? So what we decided to do is look at the interfaces that had the biggest market share. And one of the interfaces that's used with OVS today to attach a VM is VirtIO. And so we chose VirtIO, and because KVM is fairly popular. There are others that you could support, but we started with VirtIO. And we said, well, we're going to start with VirtIO, and it's a virtual interface, and I sort of need a virtual interface for bare metal as well. So we just extended VirtIO to allow it to be a physical port, just like any other interface. And then when we went to go and implement the hardware offload part, we had a couple different paths to take, and we actually tried a whole bunch of them, and there's probably more, so I'll get into that in a little bit. But we had to figure out how do we plumb this into OVS without requiring us to rip up OVS and all the components that talk to it, like the connection tracker. And then the last piece was, what we began to learn is that if you want to do this right, you really need to take all the features that were in that vSwitch unaccelerated and put them in the data plane. You can have missing features not in the data plane. Maybe you don't need to hardware offload your ARP function. But if every packet needs to have this function applied to it, then it needs to go in the hardware. Otherwise, you sort of fall off the log. Where it used to be useful, but you no longer can tell how many flows are in the system, you're out. Or it used to go really fast and it was really great, but it doesn't support your tunnel type, or it breaks when someone sends in a service tag in the tunnel. Is that hardware still usable? And that was the challenge that we discovered in our sort of first attempt, is that if you don't have that flexibility, as this network evolves, you may find yourself stuck where, well, someone has decided to add some new value into the network, but the hardware doesn't support it, so we're going to have to wait the year and a half to update the hardware. That's pretty unacceptable. So the conclusion we came to is that we really needed a reprogrammable and adaptable hardware. So it's one thing to be able to program it, but we also need to be able to adapt it to new use cases, or maybe slight variations of a common theme. The number of different tunnels used today is comical. So we needed to be able to have that flexibility so that when someone decided to reuse some tag for some other purpose, that the pipeline wouldn't break. Similarly, with an important feature that we put into the hardware was to be able to do connection tracking. And I'll talk a little bit later about the implications of adding that feature in a bit. But those are the two types of areas that having this reprogrammable hardware really helped out, was being able to satisfy those two requirements without falling out of the hardware completely. So in the virtual environment, this was the goal that we set out to achieve, and I think we've achieved it. The idea that, all right, I'm a cloud service provider and I have a bunch of VMs and they're running live and making me money and everything. And what I'd really like to do is I would just want to take those VMs and, just like my regular life where I'm live migrating them all the time for different reasons, I just want to live migrate those existing VMs over to a new server, and the VM doesn't know it, but that server is a lot cheaper for me to run because I'm using fewer cores on that server, and I can also support a much higher throughput and a lower latency on that VM. I may choose to monetize that or not, but I get the benefits of hardware offload without having to have my end customer change their VM. And what we discovered was changing that VM software is very difficult. It's sometimes more difficult to change that software than to change hardware. And so having that capability is compelling, and that's what we wanted to achieve, is to minimize the change. And the other benefit that you get out of this is once I make that switch over, I can now, just like with SRIOV, I can hardware isolate those VMs. So I can say, all right, this VM, I just moved you over, and you can get higher performance, but I'm going to limit your packets per second and your throughput in hardware. So it's a hard limit. It doesn't cost me any extra cycles to go and enforce that. And it lets me give, it makes the VM really think it has a virtual port. It has a real physical value to it, even though it's completely virtual in the cloud. And so the end customer has no idea anything has changed. They could potentially pay more to get more performance, and the cloud service provider saves a bunch of cores and has a little bit extra control over how each of those VMs use up the bandwidth that they've allocated. And I can do the same thing on the bare metal case. So in bare metal, I had a server, but I can't put anything on it because I sold the whole server. So I use a special top-of-rack switch, or I use an appliance to virtualize that server so that server can talk to everything else in the network. It might be other bare metal servers, it might be a VM, but to do the virtualization, I had to add a bump in the wire somewhere in the network in order to be able to virtualize it. And so with the same card that you had before, it's almost the same case, except it's almost like you had one big VM that's just running on that whole server. And I can run the same open vSwitch on the card and give that bare metal server the same sort of services as a VM. And if I'm an end customer buying bare metal, and then next week I decide I want to move my function to VMs because they're cheaper, or I don't need the bare metal service anymore, it's easy for me to move it around because it's the same interface. And I've taken that virtual router that used to be sitting in the network, and now I've put it into right to the edge of that bare metal. So I know that I have enough bandwidth, I know I can handle the packets per second, so you get a much more predictable network as well. All right, so now we've sort of gotten where we wanted to get, which is I have OVS in a NIC card, or an accelerated OVS in a card. How do I get the information from the OVS into the card so that we can have a fast path and a slow path? And we started and still use TC-Flower. What we found with TC-Flower, though, was that when we added the connection tracking, it was too slow to update new flows per second. When OVS is running at the edge, it's basically tracking every TCP connection. So every time a new TCP connection comes up, the packet goes to the slow path, has to be processed, and push a new rule down into the hardware. And the CSPs today are used to having a high packets per second update rate, maybe because they're using DPDK or some other mechanism. And so the TC-Flower is getting sort of in the way. So we still support TC-Flower, but in addition, we have looked at the existing Megaflow interface from OVS. What we did was, it's a better picture, we took the Megaflow cache, and, oh boy, I don't know how to use this thing. We took the Megaflow cache right here in the middle. So I guess everything on the top here is existing. We didn't change. And what we did was when a new packet came in, it gets processed by the Megaflow cache per usual. It gets applied all the different OpenFlow rules that are in there. And then once it was understood how this packet should be forwarded, we took the intelligence of that, basically the end tuple of the match and all of its actions, and we pushed it into the hardware flow cache using a device driver that we had. And this gave us much higher packets per second, connections per second than what we had in the past with TC-Flower. And it was a nice improvement in terms of performance without having to go and sort of forklift change OVS in lots of different ways. And so, it was sort of better than TC-Flower in terms of updates per second. And it was simpler because we were able to remove a bunch of kernel dependencies that TC-Flower had put upon us. And it was able to leverage a new hardware feature that we added that made connection tracking work better. And my cartoon for this is that I know I said all or nothing, but actually for connection tracking, we're not there yet. So what we do is when a new TCP flow comes in, we are still punting that first SYN packet up to software to be processed. And what that allows us to do is go and program the fast path to say, like, all right, not only do I know that this TCP connection is coming this way, but you should expect another connection coming in the other direction. And so I might still be hitting the software a little bit, but I'm hitting it much less because now I can do the rest of the connection in hardware, so that when that response comes in the other direction, I can fast path it directly. And when subsequent packets come out of the VM, I'm tracking that connection cradle to grave inside the hardware. And so I'm not going back and forth into software to having to handle every different TCP flag that's happening and changing the state in software. I've moved all of that software into hardware. And that was a big thing that we could do because our hardware was flexible. And we could go and say, well, we need something stateful. Is that okay, hardware? And we were able to put it in there. And so this is one of the things that Deb will talk about is, in general, it's hard to change software, and sometimes it's impossible to change software. And so we had to build a solution that would go faster without a whole bunch of changes. To compound on top of that, this market is moving really quickly in terms of new features that are being added. And so we needed a pipeline that could be changed and could be changed more rapidly than the regular hardware cadence. And I have 4 minutes for questions, right? Yeah, okay. So, Deb will go into this in more detail in the next section. Questions?
Yeah, we have about 4 minutes for questions. So if you have a question, please come up to one of the mics.
I did. I guess I was a little confused about why the SYN packet had to go up to software. So is the connection tracking, is it just basically looking at the flags in the hardware, or because I guess I usually think of the way that the OVS is designed, the connection tracker can be kind of a black box that you feed packets into, and then you just get flags that indicate what the state is.
So it has to go up and back into software because the rules that might get applied as to what is a legal packet or not might be fairly complex. And in the ideal case, we could have also embedded those rules into the hardware to be able to do that lookup. But it was just easier to take an unknown packet. It might be a packet that we don't even know how to connection track. It might be something else like DNS. Send it to the software and have software do the more complex slow path lookup like you have in regular OVS. So at that point, the difference between sort of hardware, connection tracker and hardware and the connection track in OVS is once we've established that connection, we no longer are setting out those flags. The black box of the connection tracker moves into the hardware.
Okay, thanks.
All right, let's thank our speaker.
Thank you.